hopefully 5 minutes, and they can catch up what they will be missing. It's a bit unfortunate. So I'm really happy to welcome Musa here. I have been following some of your publications. So when I invited him for this workshop, I was actually hoping that he will talk exactly about this. So I'm really happy. So he's a professor right now at KTH Royal Institute of Technology, and the floor is yours.
Yeah, thank you very much. And thanks a lot for the invitation. I'm very excited to be here. So yeah, today I just thought of talking a little bit, going back to modal logics, which in a sense have existed long before, the hyperlogics have been introduced, and then maybe trying to see through the lens of these logics how we can represent some kind of security properties that we're after. So let me. Okay, this seems like a pattern today. Okay, fantastic. So. Yeah, just to go back to where how Boris started the talk. So I'm also one of those cases where I started very much trying to apply formal methods for security and kind of got disappointed a little bit. So in the end, today I'm doing a completely different thing. So very much sort of using program analysis for security, but notions of that we like a lot, like soundness and completeness, we just put those aside, and then the level of success here is measured by the actual attacks, the exploitable one. Think of remote code execution vulnerabilities, for instance, that we find in real code. So I have a group at KTH called LangSec. It stands for Language-Based Security. It's this area where you try to get problems from programming language community and try to apply those to solve security problems. So yeah, so we're working on a bunch of topics here. So language-based security is the core one, but then we're doing a lot of web security, IoT app security recently, a lot of software supply chain security as well. But again, sort of foundations of computer security is what I started with, and they always come back and back. So, what I thought of presenting today is 3 things. So the first goal is to go back a little bit to all these logics that we use for specifying security properties. And what I'll try to do is use this epistemic logic and other modal logics to capture some common security properties. So now I'm not going to look at general hyperproperties. I'm going to look at properties on programs. Okay, so I look at this from a language-based perspective, and we'll sort of introduce some kind of properties. So after that, I want to go back to verification, and this sort of resonates with several talks that we listened to in the morning sessions. How we do epistemic model checking to verify some of these properties. And then at the very end, so I want to sort of, the invitation to this workshop sort of got me thinking a little bit about epistemic versus hyperlogic, and maybe probably intentionally being a little bit provocative here. So yeah, do we really need all these hyperlogics, or maybe we can do everything in epistemic logics? Don't worry, we need those, but just to get your attention. All right, so we talked about security. So what is security here? So we've got a system that should maintain some desirable properties in face of some adversary or attacker here that wants to leverage the capabilities that they have. So this is very generic sort of definition. So what are the capabilities of the attacker? Well, in a simple setting, we can distinguish with what the attacker can see. So this relates to confidentiality, and what the attacker can do. So this relates to integrity properties in the system. So this is known as the attacker model. Then desirable properties would be what you expect. So the attacker shouldn't learn this or shouldn't be able to affect that. Okay, so very simple here. So now to decide these security properties, so this is what we mean with security of a system, we sort of recite to well-known building blocks, so confidentiality, integrity. So I assume these are known to everybody in this room, but there are a little bit more interesting properties that try to combine how integrity and confidentiality interplay with each other. So 2 such properties are called verbose declassification and transparent endorsement. Any of you have heard of verbose declassification? Just to see, I'll get back to this property. Okay, not many. So what is the problem here? Well, again, we're going back to, so now we have a bunch of such properties that exist around. So these are usually trace-based conditions, very operationally formulated. So what we're going to do here is that things that everybody in this room likes, except for Boris, which is generalized. I know he likes it too, but so they are formulated in different formalisms. They are tightly coupled to specific of programming language, different enforcement details, and so on. And they're actually understood, but are they? So what we're hoping here is to have the system agnostic framework in which we can compare the different properties. Okay. So an observation here is that when we talk about security, so we often compare the same primitive basically at different circumstances. So if I don't know the password now, so suppose you have a password checking routine, then I will never know it in the future. Okay, so in order to do this, of course, you can use the basic logic, which is propositional logic, but then you want to relate these two facts to each other. And that's where modal logic comes into the game. So I assume most of you know what modal logic is, but just a refresher here. So it's an extension of propositional logic that is really meant to basically address this dimension of, for example, connecting different propositions at different time steps, for instance. Okay, so what we do is we take proposition logic and then we add basically time connective. So we add eventually, and for all can be sort of or forever phi can be defined dually here. So then what we do is we want to give a meaning to interpret these formulas, right? So for proposition logic, we have true false, so one interpretation. In modal logic, what we do is we have a set of interpretations, and then we want to evaluate our formula in one of those. So these are called the possible word model. So relations between these words then are encoded as binary relations in this case. So just to give you an example here, can I point to this? Maybe not. Okay. So just to give you an example, so we have this graph. So this is the possible word model where the arrows sort of encode this binary relation. For example, this relation R, phi is possible in this relation R if there exists a word W prime, such that if W prime are in the relation, then W prime should satisfy phi. Okay, this means that basically phi is possible. Example here, so suppose that we have a variable x as value I at word wi. So what we can say here is that in the initial word, eventually x will be 1, that's true. It will be 2, but at word w1, it is not the case that always x will be 1, because in w2 will be 2. So again, this is just basic logic. So now, when it comes to security properties, we need basically, they very often revolve about knowledge here. So confidentiality, for instance, so we talked about this at length today. So it means that it sort of characterizes what the public is allowed to know. So what the modal logic does here, it gives an elegant solution to modeling logic in face of issues like logical omniscience and so on. So the core idea is that if I don't know something, that something is actually true in my world, so I'm making an observation in my world, this must be the case because I'm not sure in what world I am. Okay? Let me give an example here. So this is called epistemic logic. So we relate these two words through relation Ka in this case, which means that two words are in a relation if an attacker cannot tell them apart. So here is an example here. So we have these three words where Bill has either $1 or 1 billion or a little more. So if we define a relation that distinguishes whether Bill has $1 or more, then what we could say here is that basically, if we are in the first word there, then we know that Bill has $1. But if we are in one of the other two words, then we don't know that because sort of either one of the two is possible. So if we compare this to the attacker view in the programming languages perspective, or the traces that you showed before, basically what determines these relations is the observation power of the attacker. Okay, so in this case, in the first word here, what the attacker can observe is whether Bill has $1. In the second, they can only observe whether they have more than 1 billion or exactly 1. Okay, so now remember the goal here is to define security properties using this model that I just showed. So in order to do this, we define something called security creep frames, which will capture the behavior of a computer system in terms of two things. So first is capabilities. What can an attacker see? And second is permissions. So what is an attacker allowed to learn or to affect in the system? Now we have to define the structures. So basically the words here are the possible snapshot saves of the system. So think of a programming language, we execute for a while, that snapshot is basically a word in our system. Relations of timing relations are defined as usual. So we have eventually or always, and then for each agent now we have 4 relations. So it's what you'd expect. We have the knowledge relation to identify what the attacker knows, given their capabilities. So it's this KAC. For integrity, we have something dual, is what they are allowed to modify, to write to. And then the permitted knowledge is basically, the knowledge is what they learn given their capabilities, and then the permitted knowledge is what they are allowed to learn. So these two things usually are the same, but they could be different. Okay, and the same for the effects. Okay, so now let's go back to the PL setting. So in this case, we have some program. We define a small step semantics operating on some stores. We have a policy, which is security labels on variables. And then while the program executes, there are some observations we're making. So usually we assume a perfect recall attack model where the attacker remembers all the observations. So now we have to specify 2 things here. So for integrity, in this model that we're considering here, there could be different models. The agent or the attacker here can determine the initial state. Okay, so they can write basically specific variables that they are allowed to write here. And they're allowed to influence basically these variables, the same variable anytime during the execution. So this is what the allowed effects. For confidentiality is the usual one. So the agents can read and they're allowed to know the contents of variables under their confidentiality label. So if we have a low variable, the attacker can look at it at any time during the execution. Okay. Good. So now, again, we have this model. We want to translate it to the security creep frames that I showed you before. So how do we do that? So the words now will be, we'll run the program for a while, we'll take the exact trace, we'll just basically identify one word. So to model now the observations of the attacker, we have a simple view function. So what the view function will do is it will take this sequence of execution, and then it will sort of project it on variables that the attacker can read. Okay, so it's very fine-grained. We use this destuttering operator to say that if the low store has not changed, we just collapse it together. You with me? Here is a little example. So we have 2 assignments here, and we are in the state where we have A, B, C, D initialized to 1, 2, 3, 4. We execute this program. So in this model, the attacker can read B and C. So if we look at the view basically of this program, then we'll see that B and C are the second and third element of the state. So we'll see 2, 3, 2, 2, 2, 3, 2, 4, 2, 4. But since we're destuttering, it's 2, 3. Okay. So we'll use this for confidentiality. What about integrity? Well, for integrity, we just define a fix operator. So here we have an attacker that can write to C and D, so the third and the fourth variable here. So here we sort of characterize it dually. We say the fix operator will take a trace and then we'll project, in a sense, what doesn't change, what shouldn't change of that trace. Okay, so these are, if you like, the high integrity variables. So in this case, the attacker can write to C and D. So the fix operator will project on A and B, which is the one that shouldn't change. So for A and B, we have 1, 2, 1, 2, 2, 2. With the stuttering, we get 1, 2, 2, 2. You with me? So nothing is just a model here. Okay, so now with these 2 functions, I have to give you the security creep Krika frame. How do we define it? So the words are prefixes of executions. So now I have to specify the relations, the 4 relations between the different words in my model. Okay. So for confidentiality, I say that W1 and W2, they are related under the attacker capability or the attacker permissions when the views are the same. Okay. So I take 2 executions, I project them, they produce the same observation. In this case, the attacker won't be able to distinguish one from the other. What about the write capabilities? Well, in my model, there could be different models. The attacker can only influence the writable variables at the beginning of the execution. So we define this in the expected ways. We take 2 words that have length 1, because we want to do this at the beginning of the execution, and the fix operator should agree. Okay. What about the permissions? So what they are permitted basically to modify? Well, here we take any 2 traces that have to agree basically. Okay. Good. So now let's get to some more sort of concrete examples. So this is a classical example, right? So you have 2 variables, P and S. S is secret, P is public. You assign S to P. So we're copying a secret variable to a public one. Okay. How do we represent this in our model? So initially, by the way, variables here are bit values, so it contains either 0 or 1. And the first component is public, the second is secret. So if we look at the bottom left, I have that P is 1 and the secret is 0. Sorry, the secret is 1 and the public variable is 0. So I execute the program, I go with a time relation in 1 step, I end up in 1. Okay. So now, since the attacker can see the value of the public variable, it means that while in the beginning you see the 2 states in the bottom, the public variable is 0, they won't be able to distinguish between the 2. When we execute the copy operation, then they have their own circle space. It's just defining the model. So this attacker views is the projection I showed before. So in the beginning, if I project on the public variable, I'll see the trace 0 on both states. Then if I execute from 1 step, then I will see the trace 0 that I had before, followed by 1. Is everybody on page here? It's kind of important to understand this notation that I'll use a little bit more later.
So the 0 is what we saw before. So
the 0 in the bottom here,
in the top.
on the top is the 0 from before, because we are perfect recall. So if we project on 1, 0, on the list 0. If we project on 1, 0, 1, 1, it's 0, 1. So we're looking at the trace prefixes. Okay, nothing surprising here. What is very nice now, and again, the same as you motivate your hyperlogics, I motivate epistemic logic. So the whole point here is to have an intuitive and beautiful specification that when you tell people, hey, look, here is what I mean with confidentiality, they get convinced. Now, beauty is sort of in the eyes of the beholder, so we may like several different things, but I'll try to sort of convince you that this is really nice. So what I can do now, and I'm trying to specify confidentiality here. So the program or the model corresponding to the program does not leak any sensitive information. Here is how we formulate it. We say that for any word in the system and any agent or attacker and any formula that you like, well, if eventually the attacker gets to know some fact phi, okay, then they knew that they were allowed to learn that they will allow to know that they will eventually learn that fact. If I'm in an initial word and I know that eventually, and sorry, no here is a bit. So I'm in the first word here, and let's say that I will eventually know that the secret will be 1. Okay? So now, if I was allowed to know that this will eventually happen from the beginning, then the program is secure. Okay? So confidentiality means that any formula that you take, if you eventually were allowed to know that formula, then you knew from the beginning that you were eventually allowed, that you'd eventually know. Let me give an example here. So, of course, this program is insecure, should be sort of rejected if this is the right definition. So this is violated at the bottom left, basically state. So that 1, 0 that you see over there. So let's assume that at that state, the attacker will eventually know that the secret is 1. Why? Because I'm in the state 1, 0. I perform one step, I go to the state 1, 1. And in that state, if you look at the red circle, the knowledge set is a singleton. So there, we know that the secret is 0. Right? But they won't know it at first because before starting the execution, the knowledge set is defined by this 1, 0, 0, 0. So in that case, the secret can be either 0 or 1. This is confidentiality. This is beautiful for me. Okay, so yeah.
What's the formula that expresses what confidentiality is?
This.
But it has to do with it.
For any word.
So you need the words to express it.
Right. But this is for any word. So I take a program, I apply this transformation that I showed you before. So each word is defined as an execution prefix. That determines a word. The time relation is ordered by prefix, basically.
Yes.
And then I define the knowledge operators. This is just the view operator. I take an execution, I project it on what the attacker can observe. All executions that end up in the same projection will end up in the same knowledge set. For instance, 1, 0 and 0, 0. So in this case, the attacker will see 0 right in the beginning. So that means they won't be able to distinguish. And then I say, take any words. If the attacker eventually gets to know some facts, so I let the system run, and then they eventually get to know some facts. Well, if the program is secure, this is because they were allowed to know it eventually from the beginning.
But only for secret facts.
Also for public, it's implicit. This is for all phi. It's sort of, it works for both. Because for public, they know it already, so it's not a problem. Question? Yeah, go ahead. It takes a while to sort of.
No, only that.
Yes.
We consider using this like the dual of ignorance because.
I will get back to that. So
yeah.
For now, I'm encoding. Yeah, I'll get back to that. That's what I did 10 years ago. I'll get back to that. Yeah. So here, I'm not talking. So even that notion, I will consider it more operational. So that's nice if you want to do model checking or maybe some more syntactic-based approach. Here, I just want to understand what secure means, what confidentiality means.
It's just the weakness I see in this is that you're saying that attacker will know that the secret is 1.
Yeah.
But it might be here, the attacker just know that there is a leakage happening and maybe can then do a refinement attack, but it does not know yet it's 1 because maybe the P was, inverting the secret. So the attacker just knows that it's leaking, but it does not know if it's leaking the value or leaking the. Just kind of.
So in this case, yeah, but in another example, you still have to apply the same encoding. So this works generically. So what you say here is that if you were to verify this, then there is this quantification as Boris is pointing out over all phi. So how would you capture this and so on? So yeah, here I just want to understand what secure means for a system. That's it. Yeah. More.
So like this whole epistemic logic thing, I think I would need to go through this more slowly. But so if you unpack this, is this like a the underlying semantics is a deterministic?
Now everything is deterministic.
So then in some sense everything boils down to a function if you unpack the semantics.
Yes.
And then if you look at really the function, an input variable is labeled as secret or non-secret. Does this then correspond to just non-interference?
That corresponds to non-interference. Well, so it depends. If the capabilities and the permissions of the attacker are the same, this will essentially be non-interference. The reason we distinguish them is because with permissions, you can say that you can model declassification or this sort of other notions as well. Because you could say that the attacker is allowed to learn the sign of a variable. But the program you're writing is maybe leaking nothing in a sense, right? So you're allowed to leak more than you're actually leaking. So you could do those kind of things. This one. Okay, so now what we do in language-based security is the following. So while you do all the fancy model checking things, so you can model infinite systems and termination and so on, from the classical language-based security perspective, people would like to use a type system, okay? Yeah, Boris has used that. I've used it quite a lot as well. And then, of course, the obvious problem here is that it's hard to prove termination, right? So you want to have programs that loop on secrets because they're kind of relevant, but then you'll have complementary technique to decide whether a program terminates or not. With the type system, classical one, you cannot do this, okay? So then what you'd like to do is you say, yeah, there are these termination leaks, but actually they're not very interesting, okay? So now you want to relax the security condition to say that basically, if the program is leaking something, and think of non-interference now for a second, and this leak is due to whether a program terminates or not, then we don't care. We accept that leak, okay? And this is important when you have a verification technique like a type system to prove soundness, because again, you can have programs that will be accepted by a type system that leaks the termination, but you want to prove them sound with respect to this condition, okay? So what you do is you assume that your attacker basically is only able to make observations when the program terminates. So what we're trying to do here, since there are many operational trace-based conditions that are termination insensitive, then we said, can we use the same framework now to characterize this termination insensitivity? Okay, yes?
Just to understand this, the attacker could be using information about the system, whether it's stuck in the loop or not, right? And you're extracting away from that. So if you get stuck in the loop, that's fine.
That's fine. That leak is fine. That's what this formula is characterizing. So when you're going, so when you get an actual program, right, that you want to verify, you'll use the type system. So the type system will have to decide if you loop on a secret, the type system will have to decide whether the program terminates or not. One solution is to never let programs branch on a secret, and then you don't need it. But those are kind of interesting programs for some people. Then they say, okay, we cannot decide termination anyways. Let's just come up with a condition that ignores leaks due to termination. Does it answer your question? Okay, so in this framework, you can model exactly that. Okay, so what you say here is that so you are in somewhere, the program will eventually terminate, and then you'll eventually know some fact. And if you eventually know some fact phi, then you will be allowed to know it eventually, that eventually if the program terminates, then you eventually know phi. Again, it's just ignoring any leaks that are happening. Program termination or not. Okay. People have tried to justify this further. There is a nice paper called Termination Insensitive Non-Interference Leaks More Than Just a Bit. So it means that if you are in a sequential setting, the best you can do to leak through termination channels is through a brute force attack. So you can only enumerate the secrets. So then they get bound saying that the leak through this channel is exponential in the size of the secret. For deterministic programs, this can be acceptable, right? If you get into the current setting, then that no longer. Okay. And then there is more. So, and again, the goal here for us, remember that, was to come up with this knowledge-based framework that takes all these conditions from the literatures, try to prove them equivalent with the formulas we have, and hopefully maybe identify some problems with what people have proposed. So different model could be what is called progress insensitive non-interference. So what does this mean? This means that now you have a system where you explicitly output values to the attacker. Okay, so now the attacker will make intermediate observations basically to what you're outputting. Okay, so now again, exactly the same story. You use the type system here. So you want to say that the leaks that are happening because of the progress of the computation, so how many outputs have occurred up to some point, you want to ignore those. Okay, so how do we do that? Well, in this framework, you can capture it in a slightly different way, which we could have done for termination sensitivity as well. We say that if the attacker will eventually know some property phi, and they won't know it because of the counting attacker, then they are allowed to eventually know the same property. Okay? We could have done exactly the same thing from termination sensitivity, as I saw insensitivity that I showed you before, but there we prefer to sort of not do it because then you have to come up with different sort of model operator. Okay, so far, very basic things. Let's get to something that is slightly more interesting, which is called verbose declassification. So now this is a property that sort of puts together integrity and confidentiality. Practical application. You have a program that is running in your web browser, and now suddenly you get some third-party code that you have to embed in your system. Okay? What you want to show is that maybe the program that you're running leaks some secret, but you accept it as the secure version. What you want to guarantee is that by embedding some other code that you don't trust in your same context, the program doesn't leak more than what leaked before. Okay? So this is a property of how integrity, you don't want low integrity data to enable your program to leak more than what is already leaking. If you think about it, it connects to what you were talking in the morning, because you have a system, you have a contract where you're happy with what it leaks in the sequential model. And now you are in a system when you have speculative execution. So you want to say that with speculative execution, my model does not leak more than the sequential model. So there are several applications of this program. Okay, so here is a classical program here that you would sort of want to reject. So you branch on a value that is controlled by the attacker. This is low integrity. Okay? And then depending on the value of that condition, then you release the secret to the public. Otherwise, you won't release it. You with me? So now, whether this program will release the secret to the public, this is controlled by the attacker, because they can set u to 1 or to 0. So remember, values are bits here. So this is something you'd like to, ideally you'd like to reject as a problem. Okay, let's go back to our model framework here, and let's see how we achieve this. It may look complicated what I've written here, but it is not. Let's just look at it together. So what we want to say is that any action that the attacker can perform, it won't cause confidentiality to be violated unless the confidentiality was violated in absence of the attacker. You with me? So if by performing some action, so we have this model operator, WAC. So if the attacker performs a write, so sets u to 1 in my example before, and there is a violation of confidentiality, the red thing is the formula I showed you for confidentiality before, negated, because it's modeling violation. So if the attacker performs an action and this action violates confidentiality, then confidentiality was violated in absence of this write operation. That's all I'm saying there. Okay? So the red thing, again, is violation of confidentiality. So now here, it's a bit tricky, because in order to capture this condition precisely, we need to talk about these formulas phi that were not a problem before, but they become a problem now. Why? Because it could be possible that some of these formulas phi you have a program that is not using any untrusted variable. You just have a program that says secret is assigned to public. This is a robust program. It's leaking the secret, but the actions of an attacker won't be able to leak more than the secret that we just leaked, right? So in order to sort of capture this precisely and not cheat by saying that phi is a formula that is controlled by the attacker, and then you sort of trivially violate this condition, we introduce something that is, I don't think is quite controversial. We call it right stability here. So what this means is that if we are in a world and then we'll eventually know some fact phi, then basically we'll know it through a right operation, eventually through a right operation of the attack. Okay, so with this condition, we rule out basically all these bad cases. So now again, here we are assuming that permissions and capabilities are different. If you want to consider them the same, then the formula becomes really nice. You say, if the attacker writes something and eventually gets to know phi, then they will eventually know phi from the beginning. This is robustness, as simple as this. Let me show you an example to sort of convince you a little bit more. So this is the program from before that we should reject. So the attacker controls its variable u. And then depending on whether u is 0 or 1, it will release the secret or not. Okay? What you see on top there is the definition of robustness I just showed. So here is what we're writing here, all possible values. So the first component is the value of the untrusted variable. So if we see here is 1, the second is the secret, the third is the public bit. Okay? So I try to write here so then you can read it a little bit for yourself as well. But here, why is the property violated? Well, if we look at the word we store 0, 0, 0, which is the one in the middle there. So now the red line is the right capability of the attacker. So the attacker could go from 0, 0, 0 to 1, 0, 0. Why? Because they can modify the untrusted. Okay? So this will correspond to performing the right operation. Okay? So now we are in the state 1, 0, 0 in this world, basically. And now in this world, we know that we'll eventually, at the world in one step 1, 0, 0, we'll eventually know that the secret is 0. You with me? So this will make true the second component. Eventually know that secret is 0. But we don't know that this will eventually be the case. Why? Because in the same state, and this is the second component there, the secret can be either 0 or 1. Okay? So what will happen in this case is that by this right operation, basically, then we'll violate the condition. Okay? Okay, maybe the details, I don't know if you were following completely, but you get the point here, I hope. Okay, so we propose these conditions. They are sort of termination sensitive in a sense. We can have the termination insensitive variance of these conditions. And then we started looking a bit in the literature, and there is some way of characterizing the same property using 4 traces. So I don't really expect you to read and understand here, but this is a very controversial condition because what is essentially saying is that as long as one of these 4 traces does not terminate, then the program is secure, is robust in this case. Okay? And then we looked at this and yeah, this is not quite right because basically there are programs that intuitively they are not robust. So look at the program over here. So if the untrusted variable is 0, then you say that if the secret is 0, then you loop forever. Otherwise, you write 1 to a public variable. Otherwise, you just release the secret. So now, if we look at the condition that I didn't unfold for you, what will happen for this program is that it will say is secure. But actually, even in the termination insensitive case, this is not this shouldn't be accepted because if the attacker sets u to 1, then you will release the secret. independently of whether, program terminates or not. So we still wanted to capture this same condition here. So in order to do that, well, if we take our condition, the termination insensitive version of it, it really rejects this program. So there is a reason why it does, but I'll save this from going through this. So in this case, when U is 0, you can learn, only when U is 0, you can learn through the termination channel. Otherwise, this is really a non-verbose problem. Okay. Then we try to sort of capture this, and then this is just to show you how crazy the formula is to just capture this condition, which arguably is simply not the right one. Okay. So what you do is really take the condition I showed you before and propose the termination insensitive version of it. So really what you see out here is the negation of the non-interference of the confidentiality condition. So if I perform a write operation and I violate confidentiality, that implies that the confidentiality could have been violated without performing asynchronous. Okay, so maybe one last one, and then I'll sort of stop on this part. So what about integrity, right? So integrity is sort of the dual of confidentiality. I have something untrusted. I don't want to affect some location that I trust. This is the sort of core idea. Well, in this framework, you can sort of nicely, in my opinion, capture it by saying that I'm in some world, and then I perform, or the attacker performs a write operation that will eventually bring about some fact phi. Well, the program satisfies integrity if eventually the attacker was allowed to bring about this fact phi from the beginning. So now what we do is we take this formula, we prove it equivalent to the notion of integrity as people have proposed it. I see a bit of confusion. I can sort of, relate to that. But if there are any specific questions, I'll be happy to. But so the main idea is that, this turns out to be a simple, in a sense, sort of formalism to characterize this problem. Okay. All right, so there is more in the paper. I invite you, if you're interested, to take a look at it. But so the take home here is that really sort of model logics are really nice sort of framework of capturing these properties, and you can do things related to confidentiality, integrity, which I showed you, robustly classification. There is another property called transparent endorsement, which is how confidentiality affects integrity, but I didn't talk about that, and other flavors. So now, one limitation here is that we only focus on deterministic systems. So non-determinism is something we really haven't touched here. So if somebody is interested, could be something nice to sort of look at. Questions about this? Otherwise, I'll move to something different. Yes.
So the goal of the paper that you're presenting on CSF is really just this specification level.
Right. So
verification.
No verification at all. It's more proposing this logic, which is arguably more intuitive, and finding issues with existing conditions.
Then my other question would be, of course, we're talking, for example, you load a third party, but there is this problem of the static analysis versus the dynamic analysis, and I was wondering how this will affect all of these definitions. You'll need the model, basically. So you need the data structure.
Right. Here is just about understanding. Then you'll have to unfold this on a real system. So for that, this is a good point, because it brings me to the verification problem, right? So this is really understanding what security means for confidentiality, integrity, classification. So yes.
So I mean, understanding.
Yes.
But is it? I'm wondering whether you can. What you can do with this. And I mean, I would believe that if there's an elegant formalism that allows you to capture everything that has been done in the literature in a uniform way.
But those are security conditions. So those talk about the semantics, right? So what you could do is maybe come up with a verification formalism that maybe uses some of these epistemic operators, and then you show that those imply this formulas. So you use some verification technique that sort of implies these conditions. There will be one direction. Because otherwise, yeah, this is a very much semantic model we are proposing here. Yes.
Okay, how do you validate the such specifications? So you look at the different formulas and
right. So yeah. So the way we'll do it is we'll take security condition like this. So this is a trace-based condition. It's very much, if you like the hyperproperty kind of condition. So verboseness, it means you have a program, you have a read and write policy, basically, and then you say that if the attacker sets some value, and then you run the system, it produces law equivalent traces, then if the attacker sets another value, it will still produce law equivalent traces. So this is the operational condition. And now we have a way of modeling this program in a Kripke structure. We have our formula. We'll show that the two are the same. Yeah, and we do have a theorem. So. Okay, good. So, but let's go back to something that is a bit more sort of verification friendly. So what we want, let's focus on non-interference again as a baseline. So we have a model, which is the program. Basically, think of some program in some language. We want a formula that specifies the security policy in terms of that program, and we want to model check the two. So this is some very old work that I did in 2011, I think. It's a class paper. It was one workshop that still exists. So what we're considering here is basically KLTL, okay? So it's epistemic logic with LTL. So in order to characterize non-interference here, so forget about the predicates there. Non-interference is saying that if I fix the public input, okay, so there is this init as v predicates, it's saying that in my model, let's take basically a specific execution where the public variables have some values v, okay? Then this should imply that it should be possible, so this is the possibility operator in epistemic logic. So it should be possible to find another trace with the same basically values of the public input, okay, such that for any value of the secret input, this is possible. Okay, so this is the shape of the formula that will capture non-interference here. So, so if every secret is possible, so this ESP stands for every secret is possible. So if I fix my public input, I sort of execute my program, I should be able to find basically a trace for any possible secret that is triggered by the same public. I'm just rephrasing non-interference. You with me? So this formula, sort of has been proven equivalent to standard non-interference definition. We consider non-deterministic systems here, but this should be just fine for non-deterministic ones as well. So for all exists, at least here should be captured just fine. And now what we want to show is that we take a program P, we take the model, so the set of executions it generates. This should entail that it is always possible that the secret is preserved. Okay.
G is globally operated.
G is always operated. Yes.
You're in a big of computation. What's the init there?
You go back. So this is an encoding of a pastime operator, but in this case, we're just interested about the initial value of the sequence. Make sense? Good. So what we showed at the time is that with a logic like this, you can model non-interference, but also various dimensions of declassification. So you can do what declassification. So in a nutshell, what you do is you don't protect the secret, but some property of the secret. So you have some phi that models what you sort of accept as a leak. You can do where declassification. This is looks like a complex formula, but really it doesn't. It's not very deep in a sense. With where declassification, it means that at some specific points in your program, you accept to leak some secret. Okay, I don't want to leak it from the beginning, but I leak it later on. So here you have this release predicate where you say, I preserve non-interference unless some condition is enabled, and now you can leak it from that point on. The when part is, you don't have it explicitly in the code, but it's some state basically that triggers, the leak of some. Anyway, this is just to mention, it's not the point. What I want to show here, connecting to some of the talks before, is how we can enforce this kind of things through symbolic execution. Okay? So what we'll do here is the following. So we'll take a program, and we have a tool that does it for Java. So we'll take the source code of a program, we'll do symbolic execution of that. Then the policy will be non-interference, so will be really a formula like this one. And then verification, what we tried two things here, and we're talking about 10 years ago. Now you're doing things way better, I hope. We try to take these models, encode it in an epistemic model checker. There is one developed at UCL called MC-Mass. Maybe some of you have heard of it. And then, surprise, surprise, we found out, yeah, it couldn't do much. Then we try to use SMP solving for doing the same. Okay, so the goal here is now we get a real program. We want to extract basically all possible executions. Okay, so what is an execution is, for what we care about is the initial state, because that's what we care about protecting, and the sequence of observations. So now in this model, we have a specific output operations that will send things to the attacker. Okay, so we need the initial state and the sequence of observations that the attacker will see. Question? 5 minutes. Oh, okay. So one abstract execution. So we use symbolic execution for that. So I guess you're all familiar with symbolic execution. So I'll sort of save the burden on going through that again. But then, so what do you do when you are in this area, right? You pick a program that is sort of cannot be verified by a type system, and you say, hey, look, I can do this, but a type system cannot. But this is actually an interesting program. So you have two while loops that sort of goes, the first one goes from 0 to secret, and the second from secret to max. So you could think of you're doing some padding basically, and you want to do it in this way. What happens with this program is that, so the max is 2 here for simplicity. If it's a secure program, it will always output the sequence 0 followed by 1. Okay. So what do we do here is first we symbolically execute the program. So now all we care about the subsequent security verification is that we want to keep track of the path condition. So what is the set of inputs that enable to reach a program point, and then the outputs that the attacker can see. You with me? So that's what we do. So this is just symbolic execution. We get to this output, we store the output expression and the path condition. These two things tell me what are all the inputs that lead to execute this output expression. Okay. Long story short is we do this, and then we get something like this. We call it a symbolic output tree, where in each node you have the output that the attacker will see conditioned by the path condition. Okay? So now you could take this thing and then you can sort of encode it basically into a model checker, give your formula as the one I showed you before, and then try to verify. This is what we tried with MC-Mass. The results not very promising. So even for very simple program, maybe at the time they will enumerating on the whole domain of the inputs. So as long as the domain was, I don't know, beyond 400, then it will just explode and never terminate. And it's acceptable because they're used for verifying, dining cryptographers and these sort of things where you have limited number of points. And then we said, I'm finishing, I know I'm late. So then we said, okay, so we have this symbolic output tree, which is the model of the program. We have these formulas. Can we just basically translate everything into a big quantifier-free first order formula and dump it to solve? We do this. So I can just show you here what we get, but we take this program and we say the program, there is some interference if I focus on some node on my tree, okay? Then if the path condition is sort of satisfied, then it should be the case that either with a different secret, maybe some other path condition is not reachable, or the output sequence that the attacker will see are different. If you know about self-composition, in the sense that this sort of relates to that kind of technique. Okay, so yeah, so this uses Java Pathfinder. So for those of you who are interested in examples and tools, I think this is something to sort of look at. And then, yeah, what we find is that, well, for these loop programs, we can do pretty well, but the loop has to be up to 40 iterations. Otherwise, the formula would explode. Could be nice for small programs, but in general, you know, yeah, it won't. Okay, so yeah, pros and cons. I think these are things you're already familiar with. What we have done recently, last year, is we have refactored this to a new version of Java, and we are able also to handle dynamic policies. So you could have things where you say, I rent a movie, then I can watch the movie, but then after a while, the subscription expires, I should no longer be able to sort of see the movie. So you can do more fancy policies. Okay, and now to the interesting part. So 1 minute for this, right? Yeah, so actually, HyperLTL came about the same time when I finished my PhD, in a sense, and I was like, yeah, there is this thing. Why don't they use epistemic logic? You know, they're coming up with this new logic and so on. And there have been counterexamples, of course. So one of the reasons I try to sort of, at least the way I understand them, is that with epistemic knowledge modality, right, you want to reason about all these alternate paths, but they are unnamed. So they are quantified under the K, the knowledge operator in a sense. So this is arguably a more coarse-grained approach. So when you do things for all exists, for all, and so on, when you want to identify, to name specific paths, then there are troubles with this approach. So hyperlogics, in a sense, are much more fine-grained because they allow you to refer to specific paths. So then while sort of thinking about this, then I started a discussion in my group and found out that there is quite some work trying to reconcile the two. So maybe some people are even in the room, probably told me before. So there has been some approach where there is this KCTL star logic, and there is the hyperCTL star. It shows that they are incomparable. So there are formulas in both logics that are not expressed. And this work proposed an extension with this pastime operator that will subsume both. So now what I want to do, and I hope somebody looks into this as well, is can we find extensions to epistemic logics that are able basically to express the hyperlogics that you guys have studied before? So we're doing some work on this. This is a minor contribution, but it turns out that if you take KCTL star, and then you extend it with propositional quantification, so you get something like KPCTL star, then this would subsume hyperCTL. And it's a bit convoluted, the translation, and we don't even know if it works at this point, but we are confident it does. So now, again, it's a matter of taste, just to conclude, right? So if you buy the epistemic account in a sense that is more natural, then you go for it. Maybe the hyperlogics account is natural in other settings, but still, I think it's quite useful to sort of try to understand, you know, the limitations and maybe propose extensions that would be able to, yeah, accommodate both logics. That's all I had to say, and I'm a bit, yeah, late. I apologize for that, but thanks very much.